For this chapter, we will be talking about action potential. An action potential is a rapid event whereby the membrane potential of a cell rapidly rises and falls. This following graph here depicts the membrane potential changes that occur during an action potential. It begins at resting levels at around -60 MV before rapidly rising to a peak point at positive levels and then quickly falling down and returning to its original negative potential. This event occurs rapidly over a span of 1 to 2 milliseconds. Action potentials are important as they are responsible for the communication of information to, from, and within our brain. Our daily activities and perception of things are all possible because of action potentials. In this diagram here, the simple reflex of a person is made possible because of action potentials. When one steps on the thumbtack, the breaking of the skin is being translated into various signals that are being passed through the sensory nerves up to the spinal cord, where the neurons further pass the information to the brain to register the perception of pain. The brain then passes the information through the motor neurons to get the person to step away from the thumbtack. This transfer of information through the nervous system is only possible because of action potentials. We will now talk about membrane potential. The resting membrane potential, denoted by Vm of a typical neuron, is generally around -65 MV, although it can range between -40 to -90 MV, depending on the type of neuron. Vm is the electrical force between the two sides of the membrane, or it can also be defined as the difference in the voltages between the insides and the outsides of the neuronal membrane. When at rest, the insides of the neuronal membrane is negatively charged compared to the outside of the membrane, which is positively charged. The neuron itself can also be said to be polarized. This negative membrane potential is caused mainly due to the presence of ions such as sodium chloride and potassium ions, whereby the concentration of potassium ions are greater on the insides of the membrane, while the concentration of sodium ions are greater on the outsides of the membrane, although the main contributor to this negative membrane potential are the potassium ions. Potassium ions want to move down the concentration gradient from the inside of the neuronal membrane to the outside of the neuronal membrane. When the potassium ion successfully leaks out of the cell, it leaves behind negatively charged anions, such as the chloride ions behind. Every potassium ions that leak out of the cell gives an additional positive charge to the extracellular membrane, while leaving behind a net negative charge to the intracellular membrane. The movement of potassium ions out of the neuronal membrane leads to charge separation across the membrane, where the outside is positively charged and the inside is negatively charged. This leads to the generation of the voltage gradient across the membrane. As more potassium ions leave the insides of the cell, a smear of negative charges are being left behind in the inside of the membrane, and the outside becomes excessively positively charged, increasing the magnitude of this voltage gradient. The voltage gradient opposes the concentration gradient to inhibit potassium ion diffusion across the membrane through the smear of negative charges attraction on the inside and the repulsion of excessive positive charges on the outside. This carries on until the electromotive force from the voltage gradient balances the thermodynamic force from the concentration gradient, giving rise to the negative resting membrane potential. However, in the case of an action potential, the reverse of this situation occurs. The inside of the neuronal membrane becomes positively charged for a brief moment, which happens very rapidly, 100 times faster than the blinking of the human eye. An action potential can be defined as a nerve impulse, or it can be termed as a spike or discharge. Action potentials are generated when a neuron sends information down an axon, and there can be various stimulus for this phenomenon. For example, as mentioned earlier, when someone is pricked by a thumbtack, action potentials can be generated in the sensory nerves to induce the perception of pain to the person who was pricked by a thumbtack. The sequence of these events begin when the neuron is exposed to a stimulus. As such, in the case of a thumbtack pricking somebody, it starts with the stimulus of a thumbtack that breaks the skin and enters in. The membrane of the nerve fibers in the skin gets stretched and sodium channels begin to open, allowing the sodium ions normally present on the outside of the neuronal membrane to start flowing into the cell as a result. As sodium ions are normally present on the outside of the membrane at higher concentrations, they would tend to want to move down the concentration gradient and flow into the insides of the membrane. This is further reinforced by the negative charges inside of the membrane, which encourages the sodium ions to cross through the channels into the membrane. This causes the membrane to be depolarized. Depolarization refers to a phenomenon whereby the cell undergoes electrical change, in which, in the case for membrane potential, is where it becomes less negatively charged or more positively charged. When the depolarization reaches a critical level, an action potential would be generated. This particular critical level of the depolarization is known as a threshold. Action potential can only be generated when there is sufficient amount of depolarization. If the depolarization does not reach threshold levels, no action potentials would be generated. The following diagram below shows the effects of injecting a positive current into a neuron to depolarize it in an attempt to generate action potential. To the left of this diagram, the initial amount of current injected is low and does not manage to depolarize the membrane to threshold. Hence, no action potentials were generated. However, as the injected current increases in magnitude, the depolarization is also increased until it manages to cross the threshold levels and action potentials were generated. This action potential generation can be explained through the use of the analogy of flushing a toilet. Try to imagine yourself trying to flush a toilet. Firstly, you will try to push the lever down to attempt to flush the toilet. In this case, if you apply a small amount of force to push the lever down a little, only a small amount of water will flow through, but the toilet will not get flushed. This is similar to applying depolarization to the membrane, whereby the threshold is not reached and no action potential is generated. However, when more force is applied to the lever, in which in this case a sufficient amount of force is applied to the lever, the toilet is now able to be flushed, and in comparison, it can be seen that the threshold is reached and action potential is being generated here. After the generation of action potential, the resting membrane potential can be restored by the closing of voltage-gated sodium channels and the opening of voltage-gated potassium channels. As the inside of the membrane is now positively charged, some of the potassium ions are being repelled outwards as they themselves are also positively charged ions. This outward movement of potassium ions to the outsides of the membrane serves to repolarize the cell, allowing it to be more negatively charged. Eventually, the membrane begins to return to its resting potential when the inside is negatively charged and the outside is positively charged again. The following video describes the process of the action potential.
A nerve impulse is an electrical current that travels along dendrites or axons due to ions moving through voltage-gated channels in the neuron's plasma membrane. Voltage-gated channels open and close in response to an electrical voltage, so they are affected by changes in electrical charge around them. When a neuron is at rest, a charge difference is maintained between the inside and outside of the cell. This charge difference is produced and maintained largely by active transport using sodium-potassium pumps. The pumps send sodium ions out of the cell and bring potassium ions in. While other channels allow some flow of potassium ions back out of the cell, the sodium ions cannot easily get back in to replace the lost positive charges. The overall result is that the exterior of the cell has a net positive charge and the interior has a net negative charge. The difference in charge between the interior and exterior of the cell is called the resting membrane potential. A nerve impulse begins when a stimulus disturbs the plasma membrane on a dendrite, causing sodium channels to open. Sodium ions flow into the cell, lessening the charge difference at that location. If the change is enough, it will cause nearby voltage-gated sodium channels to open. This allows so many sodium ions to flood into the cell at that location that the membrane there is depolarized, with the local region inside the cell having a net positive charge and the outside of the cell having a net negative charge. This affects neighboring voltage-gated sodium channels, which then open, moving the depolarization along the membrane. This moving depolarization is called an action potential. Changes occur behind the action potential to restore the resting membrane potential. The voltage-gated sodium channels close and voltage-gated potassium channels open. This allows a rapid flow of potassium ions out of the cell, repolarizing the membrane so that the inside is again negative and the outside positive. This is followed by use of sodium-potassium pumps to fully restore the resting membrane potential and to reestablish proper concentrations of sodium and potassium ions inside and outside the cell.
The phases of an action potential can be broken down into 5 parts. The threshold, where the membrane potential reaches threshold levels for depolarization. This is followed by the rising phase, which is the rapid depolarization of the neuronal membrane. Consequently, the insides of the membrane become positively charged, which is the overshoot phase. Next, the potassium channels open and repolarization occurs, forming the falling phase. Lastly, it ends off with the undershoot, which is the last part of the falling phase before the gradual restoration of resting membrane potential. The graph here shows the voltage changes that occur during an action potential. It first begins at resting membrane potential. When exposed to a stimulus, the membrane voltage begins to increase. If it does not reach threshold, the rising phase will not begin and it will be deemed as a failed initiation of an action potential. However, when threshold is reached, the rising phase quickly follows after, where there is a strong influx of sodium ions flowing into the membrane. The membrane voltage rises rapidly during this period until it reaches the peak, forming the overshoot. At this point, the inside of the membrane is positively charged. The falling phase follows after this, as the potassium channels open to allow the flux of potassium ions to flow outwards to the outsides of the membrane, causing the repolarization of the membrane. As potassium channels open, the sodium channels close as well, preventing any further movement of sodium ions into the insides of the membrane. Lastly, the undershoot occurs as the potassium channels are still open even after the membrane has reached resting potential. The undershoot gradually recovers to membrane resting potentials as the membrane ion permeability returns to its resting state. During the falling phase and the undershoot phase, it is also deemed as the absolute refractory period. During this period, no action potentials can be generated regardless of the stimulus, as the sodium channels are closed during this time frame and can't be opened. The flow of ions across the membrane can be established through the equation I ion equals G ion Vm minus E ion close bracket. E ion is the ionic current, which is the flux of ions moving in and out of the membrane. For example, the net movement of potassium ions can be represented by Ik. This ion movement is related to the conductance of the membrane, which is proportional to the number of open ion channels across the membrane. This is represented by G ion. The driving force on ions, whether it is going to move outwards or inwards, is based on Vm minus E ion, which is the difference between the membrane potential and the equilibrium potential of the ion. The equilibrium potential of any ion is defined as the electrical potential force that balances out the diffusion of ions due to the concentration differences, which is a state whereby there is no net flux of the ion occurring. So, for example, in this ideal state for this diagram, there are only potassium permeable channels. In this case, the Vm is equals to Ek. Hence, there will be no ion current flow. The ionic current will always flow as long as Vm isn't equal to E ion, which attempts to flow to bring Vm to E ion values. If Vm is more positive than E ion, the driving force is positive and ions will flow outwards. If Vm is more negative than E ion, the driving force is negative and the ions will flow inwards. For this figure, A begins with an ideal neuron at its resting state when Vm equals Ek, whereby during this time the membrane is only permeable to potassium ions. In B, the sodium channels begin to open and GNA is now larger than Gk. The opening of sodium channels drive the sodium ions to flow inwards into the membrane, attempting to bring Vm to ENA levels. In C, the potassium channels are open, and because the membrane potential is positive now, it drives the potassium ions outwards, and the efflux of potassium ions brings Vm back to Ek levels. Finally, it ends with D, which is a similar state to A. It is important to note that only depolarization to threshold potential would generate an action potential. Multiple action potentials can be generated if the magnitude of the current injected is strong enough, which will in turn increase the firing frequency of action potentials. However, there is a limit to the rate at which action potentials can be fired, and this limitation is due to the absolute refractory period where sodium channels are closed and will not open. During this time, no matter how strong the carbon injected, no action potentials will be generated. The relationship between the magnitude of the current to the firing frequency of action potentials is being depicted in this following diagram. As the depolarizing current increases in magnitude, as can be seen from the middle current to the right side current, the frequency of action potentials being fired is also increased as well. Optogenetics is a biological technique which makes use of light to control cells, mainly neurons, which have been genetically modified to induce changes through light-sensitive channels. Similarly, optogenetics can be used to study action potentials. A gene that was discovered to be capable of doing so is channel rhodopsin 2. Channel rhodopsins are a family of retinylidene proteins that has the function of light-gated channels. In the case of channel rhodopsin 2, it can absorb blue light at a wavelength up to a maximum of 480 nanometer. By introducing this gene into cells, it encodes a light-sensitive channel that is sensitive to sodium and calcium ions. Upon exposure to blue light, the channel is able to open and allow the influx of the ions, which is able to produce depolarizations that are strong enough to hit threshold levels and generate action potentials. Now we will be moving on to talk about sodium channels. Sodium channels are usually closed at resting membrane potential. They open when sufficient depolarization occurs at threshold potential to allow sodium ions to flow in. This channel is created from a single long polypeptide. When the membrane undergoes depolarization at critical levels, the configuration of the channel twists and opens, allowing sodium ions to pass through. This opening occurs with little delay, and they stay open for 1 millisecond before they close. This closure is the inactivation of the sodium channels and is what causes the absolute refractory period. These sodium channels will stay closed for as long as the membrane is depolarized. They are unable to be opened until the membrane is repolarized and is negatively charged again to around -65 MV. Of sodium channels can be impeded or even inactivated through the use of various toxins. A prime example is the tetrodotoxin, which is a toxin that serves to clog up sodium pores. This is a potent neurotoxin that is found most commonly from pufferfish, porcupine fish, and ocean sunfish. Tetrodotoxin prevents the firing of action potentials by blocking the passage of sodium ions when they bind to the voltage-gated sodium channels at specific sites. Any form of action potential that is dependent on sodium ions are all inhibited. As such, when such a toxin is being ingested, it is often lethal to the person who ingested it. Other than tetrodotoxin, there are other forms of toxins such as saxitoxin, which is found from shellfish and clams. These various toxins are all useful for experiments that can be used to study the activity, effects, benefits of sodium channels in targeted muscles or nerves. The patch clamp method is a laboratory technique that can be used to study the behavior of a single or a multitude of ion channels. This technique was discovered by the German neuroscientists Erwin Neher and Bert Sapman during the 1970s. They were awarded the Nobel Prize in 1991 for this discovery. The patch clamp technique consists of using a pipette tip to clip a certain area of the neuronal membrane. After clipping it tightly, a seal is formed between the walls of this glass tip and the patch of membrane being clipped. This results in the ions that flow through having only one path to take, while the ion channel, which is along the area clipped by the pipette through the open ion channel. The following video describes the patch clamp method in greater detail.
The patch clamp method is used to study the properties of a small patch of membrane. In this technique, a glass pipette with a very small opening is used to make tight contact with a tiny area or patch of neuronal membrane. After the application of a small amount of suction to the back of the pipette, the seal between pipette and membrane becomes so tight that no ions can flow between the pipette and the membrane. Thus, all the ions that flow when a single ion channel opens must flow into the pipette. The resulting electrical current, though small, can be measured with an ultra-sensitive electronic amplifier connected to the pipette. This arrangement is the cell-attached patch clamp recording method. A record of the current flowing through a single ion channel reveals when the channel is in an open or closed state. The currents flowing through single channels are called microscopic currents, to distinguish them from the macroscopic currents flowing through a large number of channels, distributed over a much more extensive region of surface membrane. The technique can be used to compare the response characteristics of different channels. For example, depolarizing voltage pulses applied to a patch of membrane containing a single sodium channel result in brief currents, the downward deflections. The sum of many such current records show that most channels open in the initial 1 to 2 milliseconds following depolarization of the membrane. The process by which sodium channels close is called inactivation. When the membrane potential is depolarized, voltage sensors, indicated by the plus symbol, allow the channel gates to open and current flows inward. After less than 1 millisecond, the channel inactivates when an inactivation gate swings up and blocks the pore. The pore remains blocked, even during prolonged depolarization. The pore then closes and the inactivation gate opens as the membrane potential returns to resting levels. A macroscopic current measured from another axon shows the close correlation between the time courses of microscopic and macroscopic sodium currents, reflecting the opening, closing, and inactivating of channels. Most channels open in the initial 1 to 2 milliseconds following depolarization of the membrane, after which the probability of channel openings diminishes because of channel inactivation. Technical modifications have enhanced the patch clamp technique. For example, if the membrane patch within the pipette is disrupted by briefly applying strong suction, the interior of the pipette becomes continuous with the cell cytoplasm. This arrangement allows measurements of electrical potentials and currents from the entire cell and is therefore called whole cell recording. Two other variants of the patch clamp method originate from the finding that once a tight seal has formed between the membrane and the glass pipette, small pieces of membrane can be pulled away from the cell without disrupting the seal. Simply retracting a pipette that is in the cell-attached configuration causes a small vesicle of membrane to remain attached to the pipette. By exposing the tip of the pipette to air, the vesicle opens to yield a small patch of membrane, with its former intracellular surface exposed. This arrangement, called the inside-out patch recording configuration, allows the measurement of single-channel currents with the added benefit of making it possible to change the medium to which the intracellular surface of the membrane is exposed. Alternatively, if the pipette is retracted while it's in the whole cell configuration, a membrane patch is produced that has its extracellular surface exposed. This arrangement, called the outside-out recording configuration, is optimal for studying how channel activity is influenced by extracellular chemical signals, such as neurotransmitters. This range of possible configurations makes the patch clamp method an unusually versatile technique for studies of ion channel function.
Now we will be moving on to talk about potassium channels. Potassium channels serve the role of trying to correct the membrane potential and return it to being negatively charged. Unlike sodium channels, potassium channels have a brief delay before they open when depolarization occurs. This delay of about 1 millisecond coined the term delayed rectifier for the channel. Similarly to sodium channels, the configuration of the potassium channel will also be altered when depolarization occurs, despite having a short delay, to allow the passage of potassium ions. For information to be transferred, the action potential has to be conducted down across the axon. The way this happens is in a forward direction. When depolarization occurs, there is a surge of positively charged sodium ions flowing through the membrane as the sodium channels open. These positive charges act to also depolarize the neighboring areas of the membrane, pushing them towards threshold levels. This leads to them having the adjacent sodium channels opening as well. This continues in a forward direction down across the axon. The reverse cannot occur as there is a period of inactivation of sodium channels when they close after depolarization. The rate in which this conductance occurs depends on two factors, the leakiness and the diameter of the membrane. Conduction will always choose the path that offers the least amount of resistance. Using the analogy of a garden hose, water will flow through the hose naturally if there is low resistance, such as in the case of a larger diameter with few leaky pores. However, if the hose is narrow and there are many leaks in the hose, the water will flow out through the leaks instead. Another way that will increase the conductance is the myelination of the axon itself. Myelin is a fatty substance that surrounds the outer area of the axons, which forms an insulating layer. Increased myelination leads to reduced leakiness as the current can't flow out of the axon due to the myelin blocking it. This results in increased conductance where the current will flow inside the axon instead.